Brian Staten, Project Manager at Robust Haven, and we designed the transmission control shift module. This is LeBlanc Meneses, our programmer, and then back here we have Jason Scher, the designer and creator of the PCB board, and also helped me integrate all the hardware. All right, this is the LabVIEW simulation that we created to analyze all the logic of the microcontroller and what our program is doing as we developed it. It goes between 0 and 5 volts, which represents 0% of the throttle being pressed down to 100% of the throttle being pressed down. And this is the temperature, which goes also between 0 and 5 volts. 0 volts being negative 30 degrees and 5 volts being 302 degrees Fahrenheit. All right, this is our LabVIEW test bench that we use for analyzing the logic of the code and making sure that everything was functioning as desired. I'll start by explaining the different controls that we have up here in this box. Right here we have the range select. This is what we use to select the various gears that the car can be in. We have manual 1, manual 2, drive, overdrive, neutral, reverse, and park. Next we have the vehicle speed sensor, which we also used a lever type device to indicate it. It goes from 0 to 3000, and this is because it's actually taking the pulses off of the tail shaft to analyze what the frequency is, and then converting that into miles per hour by doing some calculations based on the speed of the tail shaft to the ratio of how fast the tires are spinning. Over here we have the distributor, which is another level, and it goes from 0 to 500. Again, this isn't the actual RPMs, this is the signal that is generated on the signal wire from the distributor cap. And there's actually 4 pulses for every revolution of the rotor. So this is basically going to be divided by 4 and then multiply times 60 to get to RPMs, these values right here. Right down here we have the indicators. This is to give us all the feedback that we need to see if the device is working right, making it real easy to analyze everything. Right here on the top row, I'll go across, you'll see miles per hour. This is the miles per hour that's calculated based on the VSS signal that we're sending out. And it's actually going to use your user parameters over here, which you have tire diameter and rear gear. And this is used in the calculation of getting miles per hour. So this is dynamic, and we can change these user parameters just like we can on the desktop so that they match up and we get what miles per hour or RPMs that we're supposed to. The RPMs, just like the miles per hour, is calculated from the VSS signal, except for this is not going to use your user parameters since it's going the other way, and it's actually going to the front of the transmission instead of your rear tires. You're going to analyze what gear you're currently in, look at the ratio of that gear, and then you're going to calculate based on the ratio of the current gear of the transmission what your RPMs are based on what your current VSS signal is. Your max RPMs is what we're using the distributor cap for. And basically what we're doing here is we have a set value that the user can input or change whenever he wants, and it's going to be whatever max rev that the engine's allowed to have. Once that max revolution is once it's indicated from the distributor cap, it's automatically going to shift up no matter what the logic of our shift parameters are at that time. So even if you're not required to shift yet based on your logic and your shift chart, if your distributor cap gets in a frequency and it actually calculates a RPM that's higher than your max allowed RPM that the user entered, then it's going to shift up, and also it will have a small delay in it so that the RPMs of the engine are able to drop and idle out to the next the RPMs for the current gear, so that you don't get a basically a shift that's going to go through all the gears instantaneously, so it doesn't go from 1 to 4 in a split second. So you should see a shift that goes up to the next gear. It will wait 3 seconds, calculate a new value, and then it will shift up again. Over here we just have indicators. Not going to go through too much of the logic here. The torque converter just tells you if the torque converter is on or not. That should only happen in fourth gear if there's not a large change in acceleration or deceleration. The pressure switch assembly is what tells you what gear you're currently in. This logic is used to give you the chart right next to it. You have the temperature of the engine to tell you if it's overheated or if it's warmed up yet. You have your throttle position sensor, which goes from a 0 to 100, and then you have the actual frequencies or the actual duty cycle that the pressure control solenoid is outputting in the 3 to 2 solenoid also along with it. And as we already covered, this is just the user parameters that they can enter, so it matches up with the same calculations as the desktop. These up here, just for our own use, the LabVIEW controls, we're having to turn off some of the conditional codes because it's causing errors if it doesn't have an actual input at that time. So we're able to turn off those structures and then turn it back on when we're actually getting inputs. So we'll start off here. We'll drop it down to 0 degree, 0 frequency for the VSS. This represents 0 miles per hour and 0 RPMs. And we'll ease up the gears, or we'll we'll ease up on the VSS all the way up to 3,000, and we'll show that the logic does hold. They'll go 1, 2, 3, 4. So there's second gear, and there's third gear, and then there's fourth gear. Now, to eliminate hysteresis, where it will jump back and forth between particular gears right at that shift point, there is a different set value for the downshift than there is for the upshift, and we'll show you what we mean by that. Right there you see a shift into second that happened around 22 miles an hour, and you see that a downshift doesn't happen until we got close to 5 miles an hour, and that goes for any gear, and the user is actually able to set, the specific upshifts and the downshift points. So here you see an upshift at 47 miles an hour, and then a downshift at around 24. And you can see that happen for all the gears. All right, the next thing we'll show is the torque converter lockup, and this should only happen in fourth gear, which is only occurs in overdrive, and this is to cool the engine down. So if we set the engine into fourth gear and we let it stay steady around a particular speed without changing a large degree, you'll see the torque converter lock up, and this is another user parameter that they can enter what degree of change in speed that they are allowed, and in what period of time that is allowed in. So you can see that the torque converter came on, and we're actually able to change the speed slowly, so not a lot of deceleration, but we are able to change it, and the torque converter never unlocks. But if we do a large change, you'll see that the torque converter does analyze that there was too much change that would cause damage to the engine, and it unapplies itself. And we never left fourth gear, so it's not because of that, but it was actually because of the large changes that you see in the speed. Another thing that makes the torque converter disengage is any indication that the brake has been applied. So as you can see, we're in overdrive in fourth gear, and the torque converter has had time to lock up, and now we'll apply the brake, and you see that the torque converter is immediately disengaged, so that no damage is done to the vehicle, because it's assumed that you're going to start doing a large degree of deceleration. Whenever the brake is unapplied, the time period that the user has entered via the GUI is used to calculate when the torque converter should lock up again. As you can see, it is locked up and indicated with the light right here. Next, we're going to look at the logic based on what our shift solenoids should do based on what the range select is currently in. So right now we're in overdrive, and we're going to shift it into drive. Now the only gears that are available in drive are gears 1 through 3, and as you can see, we're still in gear 4, and you might jump to the conclusion that something went wrong, but this is actually a safety net that was installed into the application to ensure that the vehicle didn't downshift into a gear too low and the RPMs jump up or spike and burn up the engine. So gear 4 is going to be held until we lower the VSS to a speed that it can analyze that it is allowed for a downshift, and then it will no longer allow an upshift into 4th gear. So we'll do that now, and we'll keep on dropping it. And right there, around 52 miles an hour, you see that it was allowed to go down into gear 3. Now, no matter how high up we go, it will not go into gear 4 because that is a gear that is not available in drive. But all of the other logic will still work. So here we are at 0. We'll move up, and there you see 2nd gear, and we still have the downshift parameters that are different than the upshifts. So you can see it downshift there at a different mile per hour. And now we'll go ahead and go through the whole range, and there's 3. And then again, you'll see that 4th gear is not allowed. So if we go to manual 2, you'll see that we have an instantaneous jump to gear 2. Not do that intentionally going down the road. I mean, that's going to be something that you put the range select into whenever you're towing. And also the transmission is going to override the shift solenoids mechanically anyway. It's going to put itself into gear 2. So we can see that here in gear 2 you shift between gear 1 and gear 2, and that is all that is allowed. And there's a set mile per hour that you have that it's going to upshift to gear 2 to make sure that there's no damage done, which happens around I think somewhere between 35 and 45. Here we're seeing it at relatively 35 or 37 miles per hour. And then manual 1, as you would probably assume, it will keep the shift solenoids locked into 1 so that the shift solenoids logic is keeping up with what the transmission does mechanically anyway. Next, we'll show you these other indicators that we have over here towards the bottom. And this one right here is the temperature. The temperature needs to be so warm to ensure that the transmission does not have damage caused to it when the torque converter locks up. Also, it notifies if the engine is overheating, and if so, it would downshift the vehicle into gear 3. No matter if it's supposed to be in 4th or not, it's going to downshift it to 3 and pulse the TCC on and off to indicate to the user that something is wrong with their vehicle, and then also to allow the transmission to cool down. The throttle position right here, we're simulating with just a power supply over here from 0 to 5 volts, and it's going to go to anywhere from 0 to 100% to indicate how far someone has the gas pressed down. So right here we have a throttle position of 0%, and we'll put our vehicle in overdrive, and we'll put it around 63 miles an hour. Now whenever we apply the throttle and we push down on it significantly, you'll see that we switch gears based just on the throttle position.
Do that again.
And then there's gear 2.
Can you do it again?
Yes.
There it goes.
So this happens throughout the shift chart. You can see that it's not a simplistic logic where it's just going to downshift or upshift at different VSSs, but there's a multitude of VSSs, several arrays of VSSs that it's going to upshift or downshift based on the throttle position. And there should be 10 different values, 10 different increments of the throttle position that will be analyzed and used in deciding when it's going to downshift. So we'll show that this happens at several different places. We'll again show that it's all the way up in 4th gear at 68 miles an hour. If we raise the VSS, you'll see a downshift to 3. This is just like someone pushing down on the gas, and wanting a whole lot of pickup. If we go up a little bit more, we might be able to get a downshift into second. And we can't quite get it, but you can see if we just lower it just a little bit, you'd already get to drop all the way down to second gear shift. So just with the user parameters entered right now, we're almost capable of getting a downshift from gear 4 all the way to gear 2, just based on the range of the throttle position sensor. And now I'm going to talk about the pressure control solenoid duty cycle indicator down here, and the 3 to 2 solenoid duty cycle indicator right next to it. So we'll go ahead and turn it on so that it's able to detect those values. And your pressure control solenoid duty cycle is in direct relation to your throttle position. And the reasoning behind this basically is whenever someone applies the throttle position to, say, 75 or 100%, and there's a lot more power being applied through the transmission and the clutch packs to the wheel, you need a higher line pressure so that there's not any slippage. Whenever you have a 0% throttle position to, say, like 15 or 20%, and someone's just mildly pressing on the throttle pedal, well, you don't want a high line pressure, because that would cause real rough shifts and squelching of the tires and wear and tear that are not necessary, because no slippage would occur anyway. Now the indicator right here is showing duty cycle, and it's at 60% right now, and that is actually the minimum line pressure that is allowed in the transmission. And as this goes down to 0, it is approaching the highest line pressure. So you just have to keep in mind that it's reversed compared to what you think. So right now we have 60% because it's basically no one's pressing on the throttle. And as we increase the throttle, you'll see that the pressure control solenoid duty cycle gradually decreases, raising the line pressure in the transmission and putting more and more pressure on the clutch packs, so you have a more stern shift and no slippage occurs. And then we'll go ahead and lower it back down, and you can see the full range that it's allowed, anywhere from 10 to 60%. The 3 to 2 solenoid right here, again, duty cycle, and this is a solenoid that is used to cushion the downshift between third gear and second gear. And what happens if, basically, say you're in third gear like we showed earlier, and we raise this up to third gear, and then you were to increase the throttle and cause a 3 to 2 downshift, and you saw the 3 to 2 right there. If you look at these RPMs, this is the RPMs of the engine, and there's a huge change in the RPMs as it goes from 3 to 2. And if you were to shift the engine from one RPM to the other that fast, I mean, it would you'd really feel it, in your tires if you allowed the transmission clutch packs to lock up that fast, because you basically, as you can see right here, 2.4 thousand RPMs, and then as we do a downshift, bam, instantly it goes to 3.9 thousand RPMs. So I mean, that's making your engine change dramatically. And what this 3 to 2 solenoid does is it cushions it. It applies the 3 to 2 downshift band, and it lets the engine catch up to it before it actually applies that lockup between the rear tires and the engine. This should be 0% for first gear and 90%. Right now we're showing 70%, so we'll just use 70%. But it's supposed to be 0% in first gear and 70 to 90% in all other gears. So we'll go ahead and put it in first gear, and as you can see, it dropped down to 10%. Turn it on. There's gear 1, showing 9%. And then as it goes into any of the other gears, it jumps up extremely to 70 or 90% duty cycle. That's our transmission control module.